Hello, and welcome to this project demonstration about Omniformer. Omniformer is a concept of idea where we are trying to form a transformer-based time segment detection model, and we are working on the LIGO gravitational wave dataset. Our aim here is to predict different characteristics of the data using the time series based data of the LIGO association, and as we'll look at the different test cases in most of the uh, simulation analysis scenarios. What we are trying to do with this omniformer is to predict the best parameters that we can have for our other statistical models that are able to detect the noise. So omniformer is not directly controlling the noise detection mechanism, but it sort of works as a hyperparameter tuning mechanism, and and also it is a way to optimize the number of samples, as we'll look at one of the test cases, further reducing the amount of data you have to process in such temporal data sets. So let's dive into the different aspects of Omniformer, and let's begin with taking a look at its structure. So here we have a proposed diagram of how the model will look like. So right now we have very empty boxes, various empty boxes to denote the black box phase of our project, where we don't know what exactly would be the nature of each of the layers within these models. So what you are looking here within the Omniformer window is either an LSTM model or a transformer, and the way it works is that we take data from the LIGO association, we pre-process it, and the pre-processing part includes running it through a statistical tool called Omicron. And what Omicron does basically is it runs through the temporal data and finds any triggers or this time segments of data that you can define, within which the different parameters that we have entered match. So say for example, if you want to detect all the components of the signal where the noise or the signal SNR value was above a certain threshold of say 5.5, then Omicron would compile the list of different triggers and their data throughout that run of how much ever long you want, and then it would give you the output triggers. So what we do in the transformer or LSTM is primarily work on these triggers. We create a dataset using multiple triggers associated from multiple auxiliary channels, basically our source of noise. And also we take the main channel or the strain channel of the LIGO detector as the reference for our signal, that is label 0. And what the LST model does now is it goes through the different time segments, and usually there are like hundreds of different auxiliary channels working in sync with the main channel at any given time, and there's always some or the other point of disturbance in the whole interferometer system, and this leads to there being a lot of activity in the dataset at any given second. Uh, what we do here is that within the given sampling rate, that is 16,000 hertz, we try to identify is there any specific behavior between the noise in the main dataset or the main channel, the strain channel, where we are actually doing the detections of the astrophysical nature, and between the noise present in the auxiliary channel. So what we can do here as one of the test cases or one of the aims of this project is to give out channel importance ratios, where we try to rank the different channels or the auxiliary channels based on the amount of noise that they have given in any particular time segment that we give. Now this is very important because these auxiliary channels, they are fundamentally different sensors. So one of them might be measuring something like the humidity, the environment, factors like pressure, temperature. So what we want to understand here is what are the main components that are producing the noise within the LIGO interferometer, And we can use this inference in two ways. First of all, it would definitely help in further improving the design of the interferometer itself. We can go in and put environment monitoring systems. We can further improve our environment control systems. And environment is just one of the factors. We have magnetometers, we have seismic activity detectors. There's a lot of different factors that work around the main channel. And the other important aspect is that although you are able to tweak the design a bit here and there, there's always going to be some or the other form of transient noise, which is mainly what we are working here. That is not statistically repeating, but it is erratic in nature and sometimes presents out of the blue. So the other big benefit of this project would be that it would help us to remove those noises, even though we cannot prevent them, but we might be able to clean them from the main channel if we are able to characterize the nature of that noise. And the omniformer might help us to understand the nature of this noise signals based on what are the most frequent noise behaviors. Now this would mean a couple of things, like what is the SNR values of the noises, what is the frequency of the noise, which is a very important factor when you are removing noise from signal. Another big thing would be finding out the time segment. So how long is this transient noise lasting, and is it repeating at all? If so. So these are some of the test cases of the use cases of the project. And what Omniformer is not just this transformer or this LSTM model, because on its own it's not very optimized to work on temporal data sets, and it won't give out as good of an output as we want, given the high sensitivity required by the LIGO interferometer. So we need to further improve that model, and we need to do it in a way that is not very compute consuming, because the transformer model itself would take a long time and a lot of computing resources to train on the data set. So to keeping that in mind, that we need to optimize the model first of all, and also we need to improve the performance of the model. We can do something such as where we want to have a feedback loop between our output in between the run, not once the model is trained. And as the model is training, using reinforcement learning, we need to improve the performance, or I would rather say feedback learning rather than reinforcement learning, improve the performance of the model. And the role of the hypernetworks come there. This series of smaller models, how they work is that they're all connected to one another, and each of them takes the output from a certain batch of layers from the LSTM or transformer model and runs it through its own model, and then feedbacks it back to the transformer model's input as a score. So say for example you have 65 layers in the transformer model, then at every say 10 layer you have hyper network node, and what it would do is it would basically in supervised learning mode, it would give the feedback, like how many samples have been correctly identified, as for example a very simple scenario of binary classification as noise versus signal. And based on this score, we would feedback it into the input of the transformer, and then only for the first 10 layers we are already having a feedback loop. And this would mean that the error that is that would have usually propagated throughout the entire model would be halted at that point, and we would save a lot of compute in terms of not having to retrain the model every single time. Now, running the hypernetwork model does include some challenges, because if you add multiple feedback loops throughout the system, then you are creating a very high bias of your input in the system, because at every point you are trying to tune down the parameters, and this would affect the learning curve a lot. One way to mitigate it would be to add randomness to the hypernetwork. So we allow the errors to mitigate through the model, at least for some layers, at some random point of time. This would not only uh, decrease the overfitting, but it would also improve the model's performance, because now it is able to understand, say for example, the error propagated in the worst case scenario throughout till the last layer. Then the model is able to identify the errors, and it is characterized as its error. So we are also kind of improving the model's performance by adding this noise or simulated noise. uh, so that is all about the hypernetworks. But again, to run the hypernetworks, which are an independent model, there's no way to optimize the hypernetworks once we have implemented them. Sure, we can work around with the number of layers we have within the each nodes of the hypernetwork, but apart from that, there's no way to tune down its weights. Either you have to do it manually once the entire run is done, but even that is quite compute inefficient. So what we would do is we would add another agent of optimization uh, called a meta optimizer. And we call it meta optimizer because how it works is that the output from the omniformer or the transformer or the LSTM model is taken into this meta optimizer, and the meta optimizer works purely in supervised learning mode. And what it does, it creates a score table for the entire run, or at least a sample of the run. And then based on the different tunings that we have done throughout that time, so we are also keeping a record of like how many layers are changing their weights actively throughout this run, including the hypernetwork model and the LSTM model, and what kind of output we get for that. So is it a positive change or a negative change? Now this whole record is observed by the meta optimizer, and based on the different trends that it identifies, so what changes were beneficial, what changes reduced the time complexity, what changes were not good. So it uses all of those knowledge to feedback back into the hypernetwork models, not directly to the transformer models, because we don't want to affect the training of the transformer models when it is once at least a whole sample set is done. So it would simply tune the hypernetwork for the next upcoming sample set, and the idea is that we want to go in batches of samples throughout a whole run. For example, there are multiple runs within the LIGO association: O1, O2, O3A, O3B, and these runs are nothing but large sets of data where the interferometer was working. So usually they last around a couple of months, 3 months to 6 months. And what we want to do is divide the runs into at least 2 or 3 different sample sets, and then once we are done for one of the runs, then our model would be effectively optimized and trained over at least a couple hundred times, if not more. So that's the basic idea of how the whole architecture of the system works. So far, let's talk about progress. What we have done is we have worked on the pre-processing part of the data, and let me show you the different scripts that we have used. Yes. So as you can see here, we have different scripts for different tasks. So in terms of running the most basic data fetching, we have obtained the different data sets. So what we have done is we have obtained the data for strain channel of O3A run for 96 time segments, consecutive 96 time segments, and we have also obtained data for 5 other auxiliary channels. 2 of them were at the sampling rate of 4 kilohertz, and then the other ones were at the other 3 were at the sampling rate of 2 kilohertz. And this sampling rate is decided by the nature of the sensor, not by any intermediate processing part. And so how it works is that once we get those raw data in the GWF format, we run them through Omicron, which converts them to a trigger format, or in our case we have used the HP5 format for getting the data. And any given trigger has a few rows of data about first of all the SNR, the Q value, frequency range, central or median frequency, the time segment, of course, what timestamp was the timestamp at which the trigger was generated. uh, Inherently there's no way to add channel name, but we have used pre-processing and added channel name and labels, which are two different columns. And these columns, the label, so far we have just labeled the main channel as 0 and the noise as 1, and the channel name is based on the whatever channel that we want. So once that is done, we would run that through a standard LSTM model, and then so far we have only tried to use binary classification for the label value 0 or 1. And the main problem here is that even with just 96 time segments out of 624 or something, I guess was, as far as I remember, was the total number of time segments for O3 run. Even for just 96 and only one set of parameter values for Omicron, very simple set of threshold parameters with the primary threshold being SNR value of over 6. What we have observed is that the total dataset size in CSV format is 246 GBs, and when converted to HP5 format it is still at 57 GBs. Now, due to computational limits, the basic task of just loading the dataset is crashing the system and not preventing the LSTM model from training. So as far as training the models goes, that is the major barrier so far. Although techniques like converting it into some temporal form vectors would enhance the speed of the task. One aspect that we have analyzed so far is to use a model called Totem, and what Totem does is it converts a certain segment size of the temporal data into a vector form based on the trends that it observes in that time field. And how that works is it identifies not the raw data but actually the characteristics of the data set in that time duration. So we are essentially trying to downsample the data without losing any meaningful information. And it is very important because when you have temporal data sets at very high sampling rates like what we have here, that is 16 kilohertz, there is a lot of data to work through, and most of that data is not really important. So the model, even if we have the compute resources, the model might get confused by this extra bits of data that are not actually that important. So far that's the progress of the project. Our future aim is to be able to reduce the size of the dataset still considerably, and to fetch more computing resources and run the LSTM model over the dataset. Ultimately, the goal of the project would be to have a vast dataset that has at least the triggers of one of the runs, so say O3A run, and for all the time segments. And then the other important part is to have variation in the Omicron triggers. So far we just have like all of them are at the same parameter thresholds, but what we want to do is create diverse dataset that has different parameter values, and this would primarily work as our classification model, where we try to understand the importance of what parameter gives what kind of which parameter has the highest output in terms of identifying noise as a positive feedback. And once we have that, the output of the model would then help us to say, for example, we have data from the unpublished O4 run right now, then we can better understand what kind of parameters to put into our Omicron tool to identify the noise and essentially just remove the noise from our signal in that process. So the output model, or the output form of this project, would be to have a model that would simply take in raw data from the interferometer, use predictions that it has to give out the best set of thresholds that we can have for different parameters, and that would give us a range of signals that could possibly be noise, that would have very high probability of being noise based on the previous characteristics of the noise throughout the LIGO runs. So that was all about Omniformer. I'm just going to show a simple diagram of the expanse of the data set that we have. So what I would like to focus on is the upper part is just about getting the raw data set. So we have the LIGO association, which would have different interferometers, LIGO, Virgo, Kagra, and LIGO itself has two different interferometers, one in Louisiana and one in Washington, and we call them Livingston and Hanford, and each of them has different runs. These runs would have different channels of the auxiliary channel that are each grouped by sampling rates, and and there's also the main channel to be handled. And once we have those raw data sets, the main game of parameter starts now, because once you start running on Omicron will ask you for different parameters as they are enlisted here. Let me just zoom in. So there's mismatch max, there's Q range, there's timing, there's PSD length, there's frequency range, SNR threshold. Typical signal processing parameters, what they do is just simply give you a range of, say, take for example frequency range. So it gives you an idea of between what frequency do you want to label the data as noise, or Q range, where you find the Q value and you want to, using Q transform, you want to say that between a Q value of, say for example 45 and 100, you want to based on your analysis so far, you think that would have a very high probability of being noise compared to signal. So those are the parameters that you put in. Now the hyperparameters that we can work with would be limited, because first of all, the parameters of timing, it would give you a good way to control the sliding window. So how big and small do you want to keep your sample size to be? So that would be actually this length of the transient noise, the length of the burst that it would exist in. You can typically change it, but in terms of the noise detection, it wouldn't really be in your hands, right? Because the noise is generated by the actual forces of nature. So it would have a certain range of diversion, but typically it would lie in a certain fixed range. In terms of frequency, again, the noise, it is entirely inherent to the noise. It is not a parameter that you would really control as much. You can although identify the changes in phase and amplitude, because those would change very much between different noises. And all of this that you see here, they are the output of the Omicron triggers that you get. So the output trigger of an Omicron typically has the values for all of these parameters. You have the time start and the time end. That is again just the elaboration of timing, and frequency start and frequency end, once again just elaboration of frequency normally here means central frequency or the median frequency, and frequency start and end is the threshold that you have. And the time parameter here is the timestamp actually, and the time start and end is the timing window that you have for your analysis. The phase of course is the phase value of the laser that is working for the strain channel, but in terms of the signal that we are talking here, it means the phase value of the signal of, say for example, we have a sensor. Let's just take the same example of PEM sensors. So what would be the phase value of the PEM sensor at any given time? That would be the value of the phase. Amplitude is directly the value of the signal that we have. So that is all for Omniformer so far, and as I mentioned, the limitations in computing are quite challenging so far, but it is not dead end. We can definitely do a lot of optimization to work on that, and hopefully we'll be able to train the model in a very optimized way throughout the O3 run, O3B run, and eventually O4 run. Thank you for sticking through the video, and I hope that you got to learn something new about time-based analysis using AI models, especially on gravitational wave data. In the past, there has been some research done on using machine learning models for identifying noise within the dataset of LIGO association, but so far there's been no use of actual AI models to do this. So this is one of a kind research, and I'm quite excited to see what results we get. Thank you, and